Hello, everyone. Uh, I am Michal Koutný. I work in the kernel team where I work on C groups and related stuff. And one of the partially related stuff is PSI. So I have a talk about pressure stored information in Linux. Here is what we will see today. I will start with some motivation and definitions. Then I will talk about some experiments I did for memory pressure and also CPU pressure. And then I will look slightly into the implementation and some other measurements I did, and also some user guidelines. And that would be the meeting of PSI for us and for you and for me. The goal of this presentation, obviously, is for me to explore the behavior of PSI, and also for others to provide some information how to use it and what it actually does. And also, I had some underlying questions that I was interested in. Whether the PSI metric is generally useful, or whether it's really specialized for some large-scale environments like data centers with lots of machines, specialized workloads, or whether it can be used as a generic helper for any user. So the motivation behind this, or the motivation here, are some questions that users ask. Often they ask how to pre-allocate their caches to avoid OOM, or to be nice to other users in a shared environment. Another kind of question is when they have some reclaimable data, the applications. So how do they learn when to shrink those data? And another question is that is related to CPU pressure. For how to recognize how much CPU time was consumed by handling IRQs. So these are the questions that I learned from people. And then there is what PSI came with. Originally, when it was introduced, it's already several years ago. So one of the motivations was to prevent thrashing by detecting it and killing processes early instead of OOM. Or that was the use case in the data centers when the operators try to fit as much, they try to fit as much as possible onto their hardware to properly utilize it and measure how to control the pressing is this PSI metric. So I see there, at least I perceive it, that there is little mismatch between these two aspects. So here, finally, the definition, or here I actually want to seek some feedback from the audience. So have you heard about this mechanism, pressure store information in Linux before, not from this talk? Raise your hand, please. Okay. So there are around 10 people. Okay, and have you saw any values of the PSI from a system? Okay, so that's like 1 or 2 hands. Yeah, so I think it's not so much used. So here is the definition first. That's a textbook definition. That's the proportion of time a set of processes is stalled due to resource scarcity. So ideally, all processes would execute without waiting. But some of the resources, for example, the memory or the CPU, or also waiting for the I/O, there can be it's not always available. So so we measure the time when the processes are blocked when they could run. And it's important also to say that it's defined over a set of processes. And in this case, or thanks to this, we can distinguish two types of the PSI metric, which is some PSI, which means that some processes of the group are blocked, and full PSI, which means that all processes of that group are blocked. which is worst situation. It's illustrated on the picture below. Here, the group is only with 2 processes, but we see that the full PSI actually is a subset of the sum PSI. And although the group, I didn't say what is the group of the processes, so it can be either like all of them, which is called global PSI, or it is a C group that's a group of processes, for example, in a container. So now let's look at some values. Or how can you actually look at the values? So it's exposed, the global pressure is in proc file system. The C group pressure is exposed in each C group directory where there are respective files for each resource. And the value that you can get from there is this proportion, or I said is the proportion of the time. So it's some value between 0 and 1, or actually between 0 and 100%. And we can imagine it's like continuous, or it's sampled. But what we get here from this file is the average or averages of these samples over time, over the last certain number of seconds. And also there is a total sum of the idling time of the group. So, and because of these averages, these numbers that we get, they are filtered. We cannot see some high frequency events or developments. Yeah, so this is the API. We can read the file, and there is even possibility to register a trigger in a kernel, and then we will get notifications from kernel when a threshold of a pressure is hit. So first, the memory pressure. Actually, why can we get memory pressure at all? Because, for example, when a process needs to allocate memory, it must swap it in, or it must wait for reclaim, or stores during allocation. I will not talk about this. And there's usefulness of this metric. I think we can go to the experiment. So the experiment, I had a simple setup with this triangle of 3 C groups. The important one is the blue one, which I call a measured service, which shares together one slice with the parent C group with a pressing service. And the configuration here was following. The measured service had 512 megabytes of memory as a working set, and another 512 megabytes as a cold memory. This is anonymous memory. The pressing service was either a DD process, so it was copying some data which would go into page cache, which was again 1 gigabyte of memory, and alternatively, I used a process that did similar thing, but with anonymous memory. The trick here is that the whole test slice had a memory limit set to 1 gigabyte plus some little reserve, and swapping was now enabled. So that they could not fit both in there, so there was competition between the 2 services. So yeah, so how does it look like in the first case? So here I will present such pictures, such graphs. So we see the time goes from the left to right. At the top, we see the consumption, the actual consumption of physical memory by each of the groups. And the second row is the swap out of these groups. And the third row is the pressure measured by the PSI in groups. And at the bottom, I said that the measured service has some working set. So it's a dummy program, and I measured some application metric from this in operations per second. That's at the bottom. So we see in this case, when we had the competition between our test application and the DD, the performance is unaffected, and also the pressure. That's the blue line on the blue line in the third graph, it doesn't change. So the pressure actually was only in the DD group because it was reclaimed because it was only page cache. So here is nothing interesting. Second case is where I changed this DD process for process that allocates anonymous memory. And we see here at the bottom that our application was subject to some swap out, which affected its performance. We see there is a drop in this application metric. And we also see that the pressure measured in the C group, the blue line, also grew. What I want to mention here that we see that it reaches around 30% of the PSI. Here it's a thumb pressure, but the application was single-threaded, so one process, it doesn't matter. It's 30%, so we could expect that, okay, the application would spend 30% of time ineffectively, so maybe it should be like 60% of the performance. 100 minus 30, 70%. Should be 70% of the performance, but we see that the performance dropped more, which means the application perhaps was not limited only by memory. But yeah, just from this pressure number, we cannot say that much about the performance of the application. It's just a number that we must take in some context. So I had this first this example when I could see actually that the pressure metric somehow works. Then I thought, okay, it's interesting to see what happens if I disable swap, because I wanted to make the pressure. I wanted to make the competition tougher. So we can see that on the second line, the swap line stays at 0. Swap was disabled, and we see some intermittent drops in the performance of the application, which yeah, that was just non-deterministic, and we see that the PSI somehow smoothed these performance drops, and it was around 2.5%. But yeah, as previously, this 2.5%, I cannot say much about relation to the performance of the application. So next example is this, where I decreased the reserve that was allocated for the whole slice even more. And what we see at the bottom, that the application was executing, and suddenly, first it dropped slightly, and then it doesn't exist anymore. That's because OOM happened. And here I wanted to check what would we see in the pressure. So we see that actually the pressure, as measured in these experiments, the blue line for the pressure in the application stayed at 0. So we saw no pressure increase, and just OOM hit the application. So in this case, I would say the C group's pressure is not so useful predictor of incoming OOM. Perhaps the application should watch the pressure inside the limited C group, the C group that has the limit, for example, the test slice, which you see is the green line. So the pressure was growing. But again, I will show you next picture, where this is actually the very same setup with everything stayed the same. I just rerun it again, and we can see that the application, again, it ran longer, and eventually it was also killed by OOM. And the pressure here, it started to grow, then even started to drop a bit, but eventually the competition between the pressing service and the application led to exhausting the total limit, and the application was chosen for the killing. So here it could be some kind of predictor, or the application in this case could use the information, for example, to shrink its caches and prevent the OOM in this test. But again, the value here is between 2 and 4%. So it would need some calibration for the particular application, what it means. And also, as we saw previously, this was very model situation when it was not deterministic. And so it was not deterministic. So I would say this information is also kind of statistical that we get from PSI. Now, that was about the experiments with memory pressure. Then I wanted to look also into the CPU pressure, because the concept of the PSI can be used also for other kinds of resources. So the CPU pressure is again similar to memory, because the process that is in runnable state may not always run on a CPU because the CPU is busy. For example, by processes from another group or by handling IRQ. And I will delve into that in further slides. So again, the test setup was the structure was similar. In this case, my dummy application was really dummy. It was just a dummy loop writing to /def/null, and it was running in 4 tasks, 4 threads. The pressing service was same like this, or I had dummy soft IRQs generated on particular CPUs. And the limitation in this case was not the memory, but it was the CPU. So I set affinity of the whole of the whole C group tree here, or both of the siblings, to 4 CPUs, which effectively limits it to 4 CPU or 400 units of 400% of CPU. So the first experiment is that are like four tasks in our measured group and 4 tasks in the pressing group. And we had only 4 CPUs available. So here, what's best to look first is the blue line at the bottom, which is the utilization utilization of the CPU by the application, which is something what you might know, for example, from the top. If you look at the top, you see how much percent certain application takes. So here, the application initially it takes 4 units of CPU, and then when the pressing service is started, we can see that the blue line drops to just 2 units of CPU because it's competing with the others, with the other 4 threads. But the total utilization of the group, that's the violet line, stays the same because the group is running all the time. And how does the PSI look? Here my expectation was that the PSI would be 50%, which did not happen, and I am not sure why. I'm not sure why. So there is perhaps there is some hidden overhead in scheduling that I cannot see here, although I don't have. Okay, so that will be next slide. Sorry. So my expectation here, it should be 50% in the full metric, but perhaps it's because there are four tasks and they are not actually throttled all at the same time. So the proportion of time when all processes of one group are all stalled is not 50%, but here it converges to some 30%, which is a little bit difficult to reason about, and some pressure is here I would say what is interesting is the green line on the top, which when we look at the group as a total, so we would expect that if we have 8 processes for only 4 CPUs, so at every time at least one must be blocked. So the some pressure should eventually converge to 100, which it might, given how high it here went after 30 seconds. So this was the simple competition of CPU work against CPU work. The second or the next experiment was the competition of CPU work as previously, but against IRQ work. So what is worth watching here is the green line at the bottom, which is the system time of our measured service. Initially, we see that there is approximately 2 CPU units of system time, which is because this dummy program that I had actually is not pure user space. When we print to def/def/null, it's actually half and half between user space and kernel. But what we see when I started the IRQ noise, that the system time, the green line, grew a little bit, and that's because by default the IRQ time is charged towards the system time of a process that was interrupted by it. So in this case, it was our application. So we see that its system time grew. What we cannot see here, that actually if we measured the frequency of the loop, how much it prints, it would decrease because the time would be spent in system handling the IRQs. And the pressure here, what we see, so I think it's just some artifacts from the system where I tested it, because the drops that you can see there, 40 seconds apart, that's some periodic noise that I was not able to isolate. So if we ignore it, I would say here I would expect zero pressure. So that's why I call it artifacts, the bumps here, because I want to go to the next experiment when I had a modified kernel. Modified means changed configuration from the default sleek configuration, where I enabled explicit IRQ time accounting. So here, if we focus on the violet line at the bottom, we see that the actual total CPU usage of our measured C group dropped around 1.5 unit of CPU, because with IRQ time accounting, the IRQ time is not charged to the process that is interrupted, but it's charged separately, and the remaining time of the process is lower. So we see that the IRQ time accounting works, and what is the expectation for the pressure? Expectation for the pressure is that we have 1.5 unit of IRQ noise, which I split into 4 threads or 4 threads on 4 CPUs. So there should be 1/4 of 1.5, which is the 37.5%. And so this is something that we might see on the brown line in the middle, which is the IRQ pressure. I spoke about CPU pressure, and the IRQ pressure is a little bit different. It's a separate metric, but I think it's still related to the CPU measurement, because it's basically, it means how long we wait for the CPU when it's handling IRQs. So here I watched the IRQ pressure, and the pressure of the group as a total approached, I would say, those 37.5%. But my expectation was that actually it should be the application approaching this, and the pressing service should be affected by zero pressure because it actually doesn't run any code. The code is only the module doing the IRQs. So here, I'm not sure whether the IRQ pressure works well. Just one more experiment here with this. When I shifted the IRQs on different CPUs, so we know the application runs on CPUs 0 to 3, which 4 CPUs, and I moved the IRQ noise to different 4 CPUs to 5, so the overlap should be only 2 CPUs. And here it looks nicer. First, at the bottom, we see that the drop in the violet line is only 3 quarters of it's 1/2 of 1.5 because half of the CPU, sorry, half of the IRQ noise is on different CPUs out of this C group, and the IRQ pressure is the half of the previous pressure, or at least the convergence to it. So here it worked like I expected. So that was the last experiment. So we saw the values. Now, I wanted to go slightly into the implementation details, but just quickly, the PSI is actually, I talked about it as it's related to C groups, but it's actually a scheduler feature. So it's hooked into scheduling events of processes because it's important to track in what state each process is. And according to the state, we can determine the proportion of time when it's idle. Sorry, not idle, when it's blocked because of waiting for resources. Here is how you can configure it, because as I said, I did some modifications to SLI configuration. So in SLI configuration, normally it's compiled in, but it's disabled at runtime. So you can enable it by boot command line option. And then also there is a pair C group granularity when you can disable PSI collection for certain C groups. And yeah, this is also interesting, but I will skip it. I tried to measure whether there is any impact of the this enabling, the runtime enabling of PSI tracking, but I used MMTest Hackbench benchmark for this, and the measurement I did proved there is no significant difference, but there was lots of noise. So what I can confidently say that the difference is perhaps below the noise of this benchmark. So take it with a grain of salt. If you know this benchmark, maybe you can interpret it better than me. Yes. So that was part of the internals. Here is some question. So actually, what will the PSI in a C group look, the memory pressure, when the C group actually does no allocations? So I was thinking about this. So I think it wouldn't there would be no pressure, but one must not forget about implicit allocations that can happen by processes. So I think we don't do any allocations, but actually because of page cache or the swap in, there are implicit allocations. So the pressure would still be visible inside the group. Then a question, will there be a pressure if there is no runnable process in the group? Runnable like not blocked, but really not running. So in this case, actually, by the definition, the PSI is undefined because it's like 0 over 0. So the PSI is not defined here, and we can watch the total idle time that would be constant. Yes, so these were some considerations I had when one thinks about the PSI. And I could not cover everything. One thing I could not cover are real-world examples because I don't know any. So here is a quick summary. So we have the definition, I presented the memory and the CPU pressure, the data I saw. I think that it's somehow useful, but still it should be treated as a statistical thing. And the actual value, for me as European, it's as useful as pounds per square inch. So this is all. Here are references. And I think I have no time for questions.